Right now, a fleet of NASA spacecraft are turning their attention to an unusual object speeding through our solar system.
Looks like they detected the interstellar visitor, 3I Atlas, that was discovered back on July 1st, 2025.
It began quietly enough. A pinpoint in the dark sky captured by the Wide Field Survey of Asteroid Terrestrial Impact Last Alert System Atlas on July 1, 2025, later confirmed by NASA, designated as 3I Atlas, also known as C2025N1, the third interstellar object ever recorded passing through our solar system. What drew attention was not just the object itself, but the revelation that this visitor was on a path brushing past the sun, moving at breakneck speed, offering both an extraordinary scientific opportunity and a stirring cosmic drama. Before we start, smash the like and subscribe buttons for more updates. 3. I-Atlas hurtles into our solar neighborhood under the cosmic spotlight. It is traveling so fast, at speeds exceeding 130,000 miles per hour over 200,000 kilometers per h according to measurements by the Hubble Space Telescope, that it cannot be bound by the sun's gravity and is on a hyperbolic trajectory, destined to leave the solar system after its brief encounter. Its origins lie in another star system. Its path is an unbound plunge into and through our sun's domain. The discovery of such an interstellar object alone is rare. The fact that it is zooming toward the sun adds layers of intrigue. At the heart of the fascination lies the close solar passage. 3I Atlas will reach its perihelion, its closest approach to the sun, around late October 2025, at roughly 1.36 to 1.4 astronomical units, about 130 million miles, 210 million kilometers from the sun, meaning that it will come inside the orbit of Mars, yet remain far from the sun's blazing surface. While it is not literally set to strike the sun in the sense of a direct collision or grazing event, the wording of "on course to strike the sun" evokes the dramatic moment of closest approach, the intense encounter where solar heating, radiation pressure, and the dynamics of an interstellar body all converge. The significance of this trajectory is manifold. First, the approach to the sun acts like a natural experiment. The object will be exposed to intense solar radiation, heat, and the changing gravitational environment in a way that few interstellar bodies have ever been observed to endure. As 3I Atlas plunges inward, its surface ices and volatile materials will begin to sublimate, ejecting gas and dust into space. Observations indicate that this process is well underway. Instruments such as the James Webb Space Telescope have detected water vapor, carbon dioxide, carbon monoxide, and carbonyl sulfide in the coma of the object. What makes this particular object even more intriguing is its interstellar heritage. Because it hails from beyond the solar system, it carries within it a record of chemical and physical conditions far removed from our local environment. Every interstellar visitor is a messenger from elsewhere, a relic of conditions around other stars, other planetary systems, potentially far older than our own. In the case of 3I Atlas, that age may stretch back billions of years, perhaps as much as 14 billion years if it originates from the thick disk of our galaxy. By coming so close to the sun, we now have a fleeting chance to study materials that might never otherwise enter our observatory's view. As 3I Atlas moves inward, its speed and path reveal the nature of its journey. The fact that it is moving faster than any previous interstellar visitor underscores its long and turbulent voyage through interstellar space, encountering gravitational nudges, star system passages, and cosmic interactions that flung it into our neighborhood. Its hyperbolic orbit signals that the sun will not capture it. Once it swings past perihelion, it will head back out into deep space, never to return. That brevity, a single fleeting encounter, injects a sense of urgency into the observations. The close solar passage also triggers observational challenges and possibilities. As the object approaches the sun, its elongation, the angular separation from the sun as seen from Earth, will shrink, making ground-based observations difficult in the week of closest approach. In fact, 3I Atlas is expected to pass into solar conjunction behind the sun around the time of its perihelion, temporarily hiding it from Earth-bound telescopes. Yet during the approach and departure phases, spacecraft and space-based telescopes can continue to monitor it, capturing data that would otherwise be impossible. The observer window is precious. Because of the sun's intense radiation and heat, 3I Atlas will undergo significant changes. Its icy nucleus will warm, volatile compounds will escape, dust will be liberated, and the structure of the object may evolve noticeably. Observations so far hint at this. Its coma is growing, its tail is forming, and it is developing sun-facing features unlike typical comets. For example, astronomers have noticed a sun-facing plume, unusual for comets that tend to display a tail away from the sun. These effects will likely intensify as the object draws closer to the sun's heat. The implications for solar and cometary science are profound. The sun, as the dominant star of our system, serves as a giant laboratory for heating, radiation, and material processing. When an interstellar object like 3I Atlas enters this environment, it gives scientists a unique chance to observe how materials formed around other stars respond to solar conditions. Does the dust behave the same? Do the volatile ices sublimate at similar rates? Are the chemical signatures comparable to those of comets formed in the solar system? By probing these questions, we gain insights into both how objects evolve in different stellar neighborhoods and how comets in our own system might have formed. Additionally, the sun's influence on an interstellar body can teach us about the limits of comet survival. Some objects passing close to the sun break apart under tidal forces or intense heating. Others survive but are altered in radical ways. Observing whether 3I Atlas remains intact, how its coma responds, and whether structural changes occur will inform models of cometary mechanics under extreme conditions. The trajectory of 3I Atlas also invites reflection on planetary defense and object detection. Even though this particular object poses no threat to Earth, its closest approach to Earth will be at least 1.8 AU, about 270 million kilometers away. The fact that such an interstellar visitor was only recently discovered highlights how much remains unknown in our cosmic neighborhood. The fact that the sun will act as a heat chamber for this visitor underpins the importance of monitoring objects that might swing through the inner system. While 3I Atlas itself won't impact the sun, the process of close solar passage reveals how solar system dynamics play out for high-velocity bodies. Understanding these dynamics enhances our capacity to track, assess, and respond to objects that may one day cross our orbit. On a broader scale, the encounter adds to our growing catalog of interstellar visitors. With only 2 previous confirmed interstellar objects, one in Oumuamua and 2 I/Borisov, this third arrival underscores that our solar system is not isolated from the broader galaxy. Objects can and do traverse between star systems. Each visit becomes a chance to sample extrasolar material without having to leave Earth's neighborhood. The fact that 3I Atlas will pass closer to the sun than previous ISOs elevates its scientific value. For solar scientists, the passage of 3Y Atlas is also a reminder of the sun's role as more than a star. It is an engine of transformation. Comets and interstellar visitors entering the inner solar system are subjected to radiation, tidal forces, and solar wind interactions. By tracing how 3I Atlas evolves as it approaches its perihelion, we learn about processes such as dust ejection, plasma interactions, electric charging of dust grains, and the behavior of rare volatile compounds under solar heat. Preliminary observations show that 3Y Atlas is unusually rich in carbon dioxide, more so than many comets native to our solar system. This could signify origins in colder, more distant regions of its parent system, or exposure to intense radiation in its travels. In terms of astrophysical context, the event sheds light on how objects can escape their home star systems and roam the galaxy. The high-speed and hyperbolic path of 3I Atlas suggests a violent ejection in its distant past, perhaps via a close encounter with a giant planet or a binary star system in its parent system. Its passage through the sun's domain gives us a time-limited window to study one such wanderer. Every measurement collected brings us closer to understanding the galactic flows of small bodies, the mix of materials carried across star systems, and the processes that shape them before arrival. The poetic dimension of an interstellar object careening toward the sun is also worth noting. Here is a small chunk of ancient material, likely formed around another star, traveling for unimaginable eons, now hurtling inward toward our star, the sun, for a brief meeting. It is a reminder of the vastness of space. the interconnection of star systems, and the fact that our solar system is immersed in a dynamic galaxy where stray travelers can drop in. The dramatic narrative of 3Y Atlas, originating elsewhere, racing at cosmic velocity, approaching the sun, receiving its solar bath, captures both the imagination and the rigor of science. One of the intriguing consequences of the close solar approach is the potential for fragmentation or disintegration. Comets that venture too close to the sun often face structural stress. Heat can crack the nucleus, tidal forces can tear it apart, volatile pressure can build up, and material may break off. Whether 3I Atlas will experience such a fate remains to be seen, but the mechanics of this process will be closely scrutinized. If fragmentation occurs, the remnants may provide an even richer dataset, each fragment carrying clues about internal structure, strength, and composition. If it remains intact, the contrast will be instructive. The sun will act as both sculptor and revealer. Because the object will pass inside the orbit of Mars, solar scientists and comet researchers are coordinating observations from spacecraft, ground telescopes, and space telescopes. The interplay between the sun, the interstellar visitor, and the observational infrastructure creates a unique choreography. As the object moves inward, the solar elongation decreases, making Earth-based views challenging. But spacecraft on the sunward side or in orbit may continue to gather data. The techniques used to monitor the object, imaging, spectroscopy, dust analysis, tail morphology, and dynamic tracking, will help refine our future capabilities for transient, fast-moving targets. The occurrence of this event also emphasizes how dynamic the inner solar system environment can be. We often think of the sun and planets as relatively stable, but when an object from outside arrives, the interplay of gravity, radiation pressure, solar wind, and thermal processes becomes vivid. Observing how dust grains from 3I Atlas respond to solar wind, how its coma expands, how tails form or shift, and how its trajectory evolves under solar forces will enrich our understanding of the sun's influence beyond just the planets. The close solar passage of an interstellar object also prompts questions about cosmic hazard and resource. While 3I Atlas itself poses no threat to Earth, it invites us to consider the full range of bodies that might cross into our inner solar system. What if an interstellar object were to approach more closely? What if one carried unusual composition or breakup potential or gas release? The case of 3I Atlas is an exemplar of preparedness and detection. We spotted it, tracked it, and now we are readying to watch what happens as it nears the sun. In the broader scheme of space exploration and astronomy, the passage of 3Y Atlas stands as a moment of convergence. Interstellar science meets solar system science meets observational astronomy. It's not just a comet or an asteroid. It is a visitor from afar, interacting with our sun and giving us data that bridges domains. The sunlight that heats its ices is the same sunlight that bathes our own world. The dust that streams away carries chemical signatures forged elsewhere. The trajectory that arcs past the sun is a path through both local and galactic space. In that way, this event is a cosmic handshake. As 3I Atlas draws nearer to its perihelion, anticipation builds in the scientific community. Will its brightness surge? Will we capture new features? Will the interaction with the sun reveal unexpected behavior? Each day of observation adds resolution to our picture. The coming weeks and months are critical. The sunward plunge will bring the object into a zone of intense interaction, and the data gathered during this phase will shape papers, models, and future mission planning. As the visitor-designated 3I Atlas continues its swift journey toward the sun, the full import of the encounter becomes ever more apparent. This object is not simply passing through our solar system, it is plunging through the gravitational and radiation field of our central star in a manner that offers an extraordinary window into both interstellar material and solar system scale processes. With each new observation, its identity as a comet-like body of interstellar origin becomes clearer while new surprises accumulate, forcing revisions of prior assumptions and enriching the scientific promise of the moment. As background, 3I Atlas is the third confirmed interstellar object, hence the 3I prefix, ever observed in our solar system. Like its predecessors, 1I Oumuamua and 2I/Borisov, it arrived unbound on a hyperbolic trajectory, signaling that it came from outside the sun's influence and will not be a returning visitor. The high incoming speed and unusual trajectory emphasize that this object is a true wanderer from another star system. The incoming path and origin direction suggest a birthplace in a region of the Milky Way that may differ substantially from our own stellar neighborhood. What makes this event especially compelling is that 3I Atlas is on a path that brings it into the inner solar system, close enough to the sun that solar heating, radiation, and tidal and dynamic forces will play a role in altering and illuminating its nature in real time. The stage is set not only to observe an object born elsewhere, but to watch it being transformed by our star. As the object moves on its path inward, it is set to reach perihelion, the closest approach to the sun, at about 1.4 astronomical units, roughly 130 million miles or 210 million kilometers from the sun. That places it inside the orbit of Mars, but still at a safe distance from the solar surface. Because the trajectory is not merely a passive pass-by, but one of significant solar interaction, the encounter is rich with transformative processes. As 3I Atlas draws nearer to the sun, the influx of solar radiation will increase. The intense heat will begin to drive off volatile materials, the solar wind will batter the outflowing gases, and dust and ice will respond to the changing forces in dramatic ways. The approach of the sun imposes several observational opportunities and limitations. The decreasing angular separation between the object and the sun's solar elongation means that ground-based observations will grow more challenging as the object gets closer to perihelion. For a time, the little wanderer will move into the sun's glare from Earth's perspective, making certain observations harder. Yet this is counterbalanced by the fact that space-based observatories and spacecraft in varying orbits can continue to monitor the object as it undergoes its solar-driven metamorphosis. Observers anticipate that this will be a phase of heightened activity, the moment when solar heating becomes a dominant force in sculpting the object's behavior and appearance. Because the object hails from interstellar space, its chemical, physical, and dynamical properties are of profound interest. Preliminary spectroscopic and imaging analyses reveal that 3I Atlas appears to be laden with water ice and shows signatures more typical of D-type asteroids rich in organics, carbon, and silicates than standard solar system comets. The presence of primordial water ice, preserved over perhaps billions of years and eons of travel, holds potentially revolutionary insights into the early chemical conditions of other star systems. Some studies estimate the age of the object to be on the order of 7 billion years or more, drawing from its kinematic origin in the thick disk of the Milky Way. If so, this is material older than the Sun and the planets, and carries the legacy of a stellar system that predates our own. The chemical inventory so far suggests that the carbon dioxide to water ratio is unusually high, and that volatile outgassing may begin earlier than for typical comets formed in the solar system. These traits hint at a formation environment that may have been cold, radiation-rich, or otherwise distinct from the birthplace of the comets we know. Some of the dust and gas released carry signatures of organic molecules and silicate minerals, suggesting that this body may share features with meteorites found on Earth, yet in a setting utterly alien. It thereby becomes a natural sample return of sorts, not physically returned, but observed with the sun doing the heavy lifting of processing. As the sun bathes 3I Atlas in its energy, the process of change begins in earnest. The introduction of solar radiation triggers heating of the surface and near-surface layers of the object's nucleus. Volatile ices such as water, carbon dioxide, and possibly more exotic compounds begin to sublimate, releasing gas and dragging dust with it to form a coma and potential tail. As the object continues closer, the solar wind and electromagnetic interactions will act upon the escaping material, possibly stripping charged particles, forming ion tails, and generating dust structures influenced by radiation pressure and magnetic fields. One of the keys to this encounter is watching how the outflow evolves. For interstellar objects, we lack a broad baseline of behavior. This is not a typical comet from our solar system. Does 3I Atlas behave in predictable ways? Does it fragment under stress? Does the heat penetrate to alter internal structure? The sun effectively becomes a probe, subjecting the object to forces it has likely not experienced for eons. Observations will look for new jets, unexpected dust emissions, asymmetric coma features, and shifts in tail morphology. These data will help define whether the nucleus is porous or dense, whether it has layered or differentiated structure, and how resilient it is under intense solar encounters. One of the salient facts about 3Y Atlas is its hyperbolic trajectory and high velocity. Because it is not bound to the Sun, once it swings past perihelion, it will depart back into interstellar space, never to return. That adds a sense of urgency to the observations. The window is limited. The very high speed implies a long, violent past, ejected perhaps from its home system by stellar encounters or giant planet interactions, then drifting through the galaxy until our solar system's gravity offered a fleeting meeting. The implications are far-reaching. The dynamics of the encounter also shed light on how interstellar objects may be deflected, heated, or even destroyed by close stellar passages. The path of 3Y Atlas through the Sun's gravitational well will modify its trajectory, angular momentum, and velocity. Observing these shifts gives empirical grounding to models of object deflection and survival in stellar environments, data that until now has been scant. What we witness with 3I Atlas is more than a solar system event. It touches on astrophysics, planetary science, planetary protection, and exoplanetary studies. From an astrophysical standpoint, the ability to study material formed around another star system offers a chance to compare the building blocks of planets there with those here. Do they share similar isotopic signatures? Do they present alternate chemistries? In short, 3I Atlas may serve as a probe into the universality or otherwise of solar system formation processes. From a planetary science viewpoint, watching how a body with foreign origin responds to familiar solar conditions helps calibrate our understanding of cometary physics, how dust and gas evolve, how structural integrity behaves under heating, how tails form, and how solar wind interacts with small bodies. Since comets in our system vary widely, and since interstellar comets are still extremely rare, this object bridges a critical gap. For planetary defense and awareness, 3I Atlas underscores that our solar system is not sealed off. Objects from beyond can penetrate, albeit rarely, and their unpredictable origins challenge our inventory of small bodies and hazard assessments. Although 3I Atlas poses no threat to Earth, the fact that it came in unannounced from interstellar space reminds us that detection systems must remain vigilant and adaptable to new classes of objects. In the context of exoplanetary systems, 3I Atlas is like a grain of sand carried across interstellar distances from one star to another. It suggests that small body exchange between star systems may be more common than previously appreciated, offering a mechanism for the distribution of materials across vast cosmic distances. That raises questions. Could organics or ices formed around one star get redistributed across the galaxy? Could this play a role in panspermia hypotheses, or at least in the mixing of prebiotic materials across systems? While speculative, the presence of 3I Atlas compels these lines of inquiry. A key dimension of this event is the global coordination of observational efforts. From space telescopes such as Hubble Space Telescope and James Webb Space Telescope, to ground-based facilities and even spacecraft orbiting other planets, the campaign to monitor 3I Atlas is broad and intense. Each dataset adds a layer of understanding: imaging to map morphology, spectroscopy to identify chemicals, dust monitoring to understand particle distribution, and dynamic tracking to measure motion and forces. As 3I Atlas approaches the Sun and passes near Mars on its inbound leg, the possibility exists for spacecraft orbiting Mars to capture valuable data, including spectrometry and imaging. While the opportunity is fleeting, it is unique. No prior interstellar object has come this close with this level of instrumentation ready. Observers are poised for capture of real-time changes as the object responds to solar forces, enabling direct measurement of outgassing onset, coma growth, tail formation, and possible fragmentation. In practical terms, this is a once-in-a-lifetime chance. The window is constrained by geometry and motion. The sun's glare will limit observations during part of the approach, and once the object recedes, it will rapidly fade and escape into the depths of space. The pace of data acquisition is high, and each week, even each day, may bring significant new revelations. It is worthwhile to reflect on what the sun itself contributes to this exploration. One might think of the sun simply as a passive central star, but in this case it is the actor that invigorates the object's transformation. Heat from the sun warms surface layers, causing volatile release. The radiation field accelerates dust, exerts pressure, and influences tail formation. The solar wind drags and shapes ionized outflows and creates interactions between the object's coma and the ambient heliospheric environment. Magnetic fields may thread through the tail and interacting region. The sun's gravity influences trajectory, altering speed and direction of 3I Atlas. In addition, the sun acts like a natural furnace, revealing invisible properties of the object. Materials that have sat in interstellar cold may sublimate for the first time in billions of years. The light from the sun might prompt dust grain fragmentation, surface cracking, and internal stress release, enabling scientists to witness processes otherwise hidden. By watching how 3I Atlas responds, we learn not only about the visitor, but about how small bodies operate in extreme solar proximate phases, knowledge applicable to comets and asteroids in our system. Beyond the strictly scientific implications, the event carries cultural resonance. The arrival of an object from interstellar space into our solar system, into the realm of the sun we orbit, is evocative of interconnectivity in the galaxy. It bridges our solar system with the vast interstellar medium, reminding us of the dynamic nature of the cosmos. Observers tracking this object feel a sense of cosmic perspective. What originated around a different star now briefly visits us, traverses the solar system, interacts with our sun, and then departs. It underscores that our celestial environment is not isolated. For educational outreach and public engagement, the story of 3I Atlas speaks to universal themes of exploration, discovery, and the unknown. It invites questions about where comets come from, how star systems operate, and how objects travel between systems. It puts into sharp relief that astronomy is not just about our solar system. It is about a galaxy of systems, ever-changing and ever-connected. The upcoming period, the perihelion passage and immediate subsequent months, holds potential for key discoveries. Researchers anticipate refining estimates of nucleus size and shape, mapping dust production rates, quantifying volatile release, and determining the particle size distribution in the dust coma. Observations will aim to capture tail morphology in both dust and ion components, measure how the coma expands, assess rotational state changes, and detect any fragmentation events. Models of cometary behavior under solar heating will be tested. Does 3I Atlas conform to known thermal evolution models, or does its interstellar heritage impart novel behavior? For example, its unusually high carbon dioxide content may lead to outgassing at larger distances, perhaps altering the onset of activity compared to local comets. If it fragments or sheds large amounts of dust, that will feed into structural models of small body strength and evolution. Moreover, the trajectory and motion under solar gravity and non-gravitational outgassing-driven forces will inform orbital dynamic models for hyperbolic bodies by measuring how its path deviates from a purely gravitational trajectory. Scientists can infer mass loss rates and directional jets. While the focus is now on the inbound and perihelion phases, planning is underway for the outbound leg. After it passes the sun and begins its departure, monitoring will focus on decay of brightness, tail evolution as solar influence wanes, and how quickly the object fades into the interstellar medium once again. The comparison between pre- and post-perihelion behavior will be especially instructive. Did the solar encounter significantly alter the object? Did it shed material, change rotation, or alter composition? These comparative data will complete the story of the encounter. In addition, the object's outward journey may intersect with other spacecraft or observational nodes. Although direct intercept is unrealistic owing to its speed and trajectory, secondary opportunities may arise for remote observations. The data gleaned during and after perihelion may inform design considerations for future missions targeting interstellar visitors should detection happen earlier next time. The passage of 3I Atlas is not only a moment of observation but a moment of preparation. The astronomical community anticipates that with improved survey telescopes, more interstellar objects will be discovered. This one acts as a test case. How well can we detect, track, characterize, and observe interstellar objects on short notice? The instrumentation, coordination, and data sharing networks being activated now are building a legacy infrastructure for future encounters. In the longer term, this event may influence mission planning. The concept of sending a spacecraft to intercept an interstellar comet shortly after discovery remains technologically challenging, but the growing database of such objects and their behavior may one day make it feasible. The springboard begins with 3I Atlas. The more we learn now, the more prepared we are for the next visitor. This event invites reflection on the scale and connectedness of our galaxy. An object formed around another star, ejected or escaped, wandering through interstellar space for eons, now enters the gravitational sphere of our Sun, interacts, and departs. It crosses the boundaries of star systems. It reminds us that small body populations are not strictly confined to one star. Material exchange is possible, even if rare. The encounter also raises philosophical thoughts about intimacy in space, that our Sun, though central to us, is but one actor in a much larger galactic stage, that the solar system is a passerby in a sea of interstellar wanderers. Observing 3I Atlas reminds us that our observational instruments are reaching into time and space, catching up with objects that carry stories from the deep past and far away. As the days toward perihelion draw closer, anticipation among scientists and observers grows. There is a sense of urgency, of opportunity, of witnessing something transient but profound. This is not an event that will be easily repeated. The alignment of discovery, instrumentation readiness, and favorable geometry is rare. The window is narrow. Every hour counts toward capturing the story of this interstellar visitor as it interacts with our Sun. In that sense, the passage of 3I Atlas is a cosmic experiment. The Sun, the object, and our observational network act together, converging on a fleeting moment. Whether the comet fragments, remains intact, or surprises us with unexpected chemistry or dynamics, the data gathered will echo across disciplines. This singular passage adds a new chapter to our understanding of interstellar wanderers, the Sun's influence, and the interconnectedness of star systems. Viewed in the larger sweep of cosmic time, this event is a moment of convergence. An ancient traveler from the galaxy's deep past meets the bright, familiar light of our Sun. An object formed elsewhere arrives, interacts, and leaves. Researchers stand ready, lenses and detectors trained, to absorb what nature will reveal. The Sun may not be changed by the encounter, but our understanding of the Sun and the broader cosmic theater will be enriched. In all, the trajectory of 3I Atlas toward the Sun is more than a passing headline. It is a meeting of cosmic scales and stories. Interstellar origin meets solar system environment. Ice and dust from afar meet our Sun's energy. Science meets excitement, and the window of observation opens invitingly for a brief but potent moment. The implications, both scientific and philosophical, are sweeping, and the experience of watching an interstellar visitor dance with our Sun is one of the most compelling chapters in modern exploration. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on 3I Atlas heading toward the Sun? We want to hear from you. Thank you for watching, and see you next time.